I think we are ready to start. So, hello everybody. My name is Roberto Lineros. I'm going to be the host of this webinar, this law physics webinar. Today we have a very interesting talk. The speaker is Álvaro de la Cruz from University of Cape Town in Africa, in South Africa. And it's going to be a very interesting talk because it's going to mix gravity, gravitational waves, and neutron stars. So a little bit about the speaker. He did the PhD in the Universidad Complutense de Madrid. And after that, traveling around the world, now is a permanent lecturer at the University of Cape Town. So the title of his talk is New Windows to Understand Gravity, Neutron Stars, and Gravitational Wave. So Álvaro, whenever you want, you can start this nice webinar.
Thank you, Roberto, and thank you to all the organizers. Good afternoon from my side. Good morning, maybe for some of you, or good evening even. Let me share my desktop. I'm gonna use PowerPoint because I would like to show you some videos, so that's why you will see me using PowerPoint. Let me go to diapositivas. As Roberto, I guess that you are seeing the presentation. My talk is going to be about new windows to understand gravity in both neutron stars and gravitational waves. Can I ask you, Roberto, if you are seeing me correctly?
Yes, it looks perfect.
Thank you. That was the only check. Good. I'm going to start with neutron stars. I'm going to try to give you a flavor about why neutron stars could be very, very interesting objects to understand what gravity is, or what is the underlying theory of gravity, let's say. We are used to know or to say that both black holes and gravitational waves are interesting fellows to understand gravity, but neutron stars, or stars in particular, have been left a little bit aside. So I would like to try to convince you, or to give you that flavor about why neutron stars could tell us something. Later on, of course, I could mention, of course, gravitational waves, and even how neutron stars could give rise to gravitational waves, and how those gravitational waves could, of course, tell me or tell us something about the nature of gravity. So the outline of my talk is more or less this one. It looks a bit long, but it's not. First of all, I will try to convince you what the tension is between what we know and what we don't know about gravity in astrophysical configurations as stars and black holes. Later on, I would like to tell you what are the tools we have to deal with neutron stars, mainly the so-called TOV equation, Tolman-Oppenheimer-Volkoff equation, and the equation of state. I mean, what is the fluid which is inside the neutron stars? Later on, I will focus on theories beyond, in my point 3, I will focus on theories beyond general relativity in the so-called FOFR gravities. Since we want to check or to test gravity, it's good that we consider theories beyond general relativity. And those theories, the so-called FOFR theories, could tell us something beyond general relativity. I will study a few things over that. And finally, my final point 4 would be about gravitational waves. So let me start by motivating a little bit why gravity is not that clear interaction when we are dealing with such strong gravitational fields as those which are supposed to be happening in stars, in neutron stars, in black holes, in any other object that you can think of. So the idea is that, well, this is of course a very naive picture about what may be happening inside a star, right? And of course, stars are places where the gravitational field is extremely strong. So that means that we can only make assumptions, or we can only develop some kind of theories about what is the nuclear physics which is happening inside. And some of the theories that are now in the market, let's say, even consider that neutron stars have like a core, a quark core. So what I'm trying to say is that we don't have free neutrons in stars. We are going to have some kind of gluon plasma or gluon quark neutron plasma. And that's difficult to study. As you can see there, in 10 kilometers, more or less, we can host like 1.2 solar masses. So that's how dense neutron stars can be. Can we constrain general relativity from neutron stars? Well, the answer is going to be yes. But before that, if you go to the right-hand side of my the slide, you can see that inside a star, roughly speaking, we could have 10 to the 12th in orders of magnitude meter per square second, versus what is around order 300, the intensity of gravity that we measure on the Earth, on the solar system, etc. So what I'm trying to say is that there's a huge difference in orders of magnitude that neutron stars can tell us about gravitation itself. The order of magnitude could be like 10 to the 6 for white dwarfs, but could be like 10 to the 12, as I said, for neutron stars. In other words, we are actually like extrapolating the validity of general relativity by 6 order of magnitudes, by 6 powers of 10, right, by a million of, multiplying by a factor of a million, when we say that general relativity works very well, in the solar system, and then later on we say that it's going to work very well in such compact and highly energetic objects as neutron stars are. Nuclear physics, on the other side, is actually only, let's say, extrapolated up to a factor 3 or 4. What I'm trying to say is that the intensities that we expect from the nuclear forces in neutron stars are only, let's say, around 3 or 4 in factors. What I'm trying to say is that both interactions, both QCD and gravitation, are ideally tested in such highly energetic environments. But general relativity or gravitation even more, because the orders of magnitude are much higher. I don't want to spend much time here, but this is, I think, a key point to understand what I meant. What about the constraints coming from general relativity? Yes, we can constrain general relativity using stars. And this is a plot about, let me for a moment like consider theories beyond general relativity, and then we can test how well general relativity works. This is what is shown here with the effective scalar coupling strength. And for several neutron stars, then yes, we can check that they do agree with the expected behavior. But I don't want to enter into details about this. This is a paper published in Science some years ago. What about general relativity? Well, in general relativity, we know that the intensity of gravity is not only related to the mass. On the left, you can see the standard Newtonian physics interaction. On the right, you can see what general relativity brings new into the picture. But what we see is that we've got plenty of neutron stars that we have been already detecting. Okay, so here you've got like several examples of neutron stars, and you see the solar masses. When you do the calculations in pure general relativity, and this is what you can see here on the right, if you consider free neutron gas, as I mentioned earlier, you can only host stable stars which are around 0.6 solar masses. And as you can see here in the plot, we do observe neutron stars which are much heavier than 0.6. Well, first of all, because neutrons are not free inside stars. If you consider that the forces between neutrons are actually affecting the nuclear interaction, QCD, then you can get to 1.5, 1.6 solar masses. And even if you consider chiral interactions, you can get up to 2.2. What I'm trying to say is that depending on the type of matter or the type of neutron interaction, if you want, that you consider inside the stars, then you can change the masses that stars can host. All those results are true within general relativity. I'm not modifying my theory of gravity. I'm just considering that general relativity is true, but that the equation of a state, I mean, what is going on inside the star is different. And as you can see, I can vary by being more and more realistic, let's say, my masses of my stars. Okay, so this is a point that is also important to establish the importance of the nuclear interaction of the equation of a state inside the star. Let me now move to the tools that we have to study neutron stars. I mean, the precise tools we have to study neutron stars. The first one is the so-called TOV equation, which is the Tolman-Oppenheimer-Volkoff equation. And this is just the equation telling you, it's a very old equation, as you can see, it's 1939. And is that when we consider not Newtonian physics, but when we are considering the full general relativity picture, then in this beautiful equation, which is a first order equation for the pressure, we can have everything, because we've got the pressure and we've got the epsilon, which is the density, if both are related with the equation of a state. And you give me a definition of the mass that, roughly speaking, is nothing but the integral of the density over the volume. With all that, you can solve the system, and then you can tell me, look, this is your mass of your star, and this is your radius of the star. And then we will get like mass radius diagrams. So we will get like one mass and one radius, that's star. So this is the beautiful result that Oppenheimer and Volkoff found in the late 30s. Once again, within general relativity. Within general relativity, this is the equation governing the evolution, not the evolution, but the existence, the very existence of neutron stars. And this is what you get, as I was saying. Like every blue curve that you can see, or every purple or green, correspond to different equations of a state, corresponds to different models of stars, let's say. I mean, of different models of interaction within the star. And as you can see, you get curves. First of all, this is a very nice result, because people usually think that, well, if it's not a black hole, then immediately you've got a star. No, this is not true. I mean, not every point in this diagram, like here, for instance, or down here, or up there, is a neutron star, or is a star. You need to be in one of the curves, depending on the equation of a state. Once again, I mean, if we are detecting neutron stars with two solar masses, for instance, like this horizontal band, only equations of a state able to predict neutron stars with higher or equal masses are realistic, right? So all those equations of state I'm pointing now will be realistic, because they will be telling us that yes, that star that we do observe is real. Equations of state which are always for any parameters below that observational result, that means that, well, you cannot explain reality, so therefore you are excluded. All those plots that you are seeing here correspond once again to calculations done with general relativity. So I'm in general relativity, and then I'm changing my nuclear interaction, let's say, inside my star. Okay, that's also a point to remark here. The other thing, as I said, is what about the equation of a state? I mean, because in the previous plot, probably you got convinced that my results are very dependent on my equation of a state. So what can we say about equation of a state? Well, we can say many different things, right? I mean, of course, you need a relation between density and pressure. You should be below the causality limit, so your velocity of propagation of sound inside the star cannot reach the speed of light. That you want, of course, to recover star, not a black hole, and that heavier stars heavier neutron stars will be testing general relativity, because we'll be telling you things about both general relativity and the equation of a state. Well, actually, this is just to mention how we measure the masses of a neutron star. Okay, and this is by the Shapiro delay. Okay, you can read more if you want about the Shapiro delay. Even in Wikipedia, you can find what is the method to determine where the mass or how much massive a neutron star is. But let me come back to equations of state. As I said, neutron stars are not just free neutrons. They are correlated particles inside, either because you consider that gluons do appear, or even because you consider that there is like a kind of plasma of quarks, neutrons, and gluons. And the more refined your calculations are when dealing with equation of state, the more realistic you are expected to be. For instance, here on the right, you can see that for a free neutron gas, I mean, if you are very naive and you say, look, I'm going to do my calculation of density and pressures using a free neutron gas, you can do it. This is an undergrad exercise, and this is what you get, this dashed line down here. But when you become more and more realistic, I mean, when you use like chiral effective theories or other approaches I will mention now, then as you see, your equations of state look very different. Okay, they are not that linear down here, but they start to have a different behavior. And this is, well, for several reasons, right? That neutron is not an elementary particle. You will activate new degrees of freedom, etc. I'm not gonna go into details, but if some of you are QCD experts or are QCD people, then you fully understand what I mean. And is that, well, I mean, reality in particle physics is not that simple, and neutrons are not free when they are in such intense density environment. Down here in this slide, what I'm showing is that four equations of state I was considering. Three of them, the stiff, middle, and soft, that you can see in different colors, have been calculated by, well, other people, not by me, using effective field theories, using chromodynamics. So this is where we are bringing, we cosmologists or we astrophysicists, we are bringing QCD people, particle physicists, right? We have also included this other equation of state in purple, which is using potential models, like, let's say, parameterizing your nuclear forces using like potentials. Okay, that's a different approach, but as you can see, well, the equations of state are similar, but they are not the same. So with those equations of state, now, yes, now we can be realistic. We can say, look, the neutron star I want to study, I'm going to assume it has this kind of equation of state. What do you get? Which masses do you get? Which radius do you get? But at this stage is where I want to open that other box. And the other box is like, general relativity maybe is not the final theory of gravity. So if you really want to use neutron stars to test interaction in nature, it's good that you consider different QCD models, but why don't you consider different gravitational theories? And maybe from the combination of both realistic QCD models with theories beyond GR, you can constrain GR. You can tell me something about the gravitational field interaction. Before that, let me keep in general relativity for a moment. This is, as I told you, the Tolman-Oppenheimer-Volkoff equation. A nice paper some years ago in 2012, those guys consider, let's modify just the Newton constant in a very naive way, just moving that the value, let's say, is not 1 with respect to the Newton constant on Earth, but is actually slightly heavier or slightly smaller than the interaction on Earth. And as you can see, within GR, if you change the intensity of the Newton's constant, then yes, then you can predict neutron stars heavier than 2 solar masses. Okay, so this is a very good exercise. Of course, this is nothing physical behind this change of the Newton's constant. It's just a phenomenological way. It's like, okay, let's move it up and down and let's see what we need, or how much do we need if we want to predict those neutron stars. On the right-hand side, you can see actually something which is very nice, and this is the intensities that we can measure on Earth, right? Like 10 meters per square second. The intensities we can measure in the solar system or in other environments, and the intensity we are measuring in neutron stars. So what that paper concluded is that you cannot change much your intensity of your gravitational interaction if you do want to predict two solar masses neutron stars. As I said, there is nothing physical here. It's just to change slightly the Newton's constant. So we are within GR, but with a kind of, let's say, modified GR only in the interaction between two masses, right? The Newton's constant. Let me now, opening this box of modified gravities. I'm going to motivate slightly why we need to modify gravity. Then I will tell you, once we open that Pandora's box, like gravity might be not general relativity, what is the methodology that we are going to follow? I mean, how are you going to calculate the stability of your neutron stars? Can you tell me if neutron stars exist within those theories? Can you obtain mass radius diagrams, and how do they look like? The second thing I will focus on very briefly, but I think that's important, is what is the mass definition in those theories? We do have mass definition in Newtonian physics. We do have a mass definition in general relativity, roughly speaking as Schwarzschild mass for black holes and for stars. But what is the mass, what is the asymptotic mass in theories which are slightly different from general relativity? I'm still in 4 dimensions. I'm still in classical theories, let's say. I'm not gonna open a box of extra dimensions, string theory, etc. So don't think that this mass definition is gonna be very different from the standard general relativity, but it's gonna include something that is gonna be interesting. I will come back to that issue later on. And then I will be presenting results for 2 f of r gravities. One is the r squared that maybe some of you heard about in Starobinsky inflation, and it also can be applied to, well, why not? If it's explaining Starobinsky inflation, it could be nice to test if that model is able to explain neutron stars. And another model which is purely, let's say, f of r cosmologically interesting, which is the so-called Husawiki model. But anyway, I will come back later on to those 2 models, okay? For the moment, let me say that those are 2 examples of f of r gravities, and that now I will motivate why we need theories beyond general relativity. Well, theories beyond general relativity, at least in the context of cosmology and late-time cosmology, like to explain acceleration or to explain dark matter if you want, even to explain inflation, as I said, for the Starobinsky model, I usually refer to as extended or sometimes modified theories of gravity. I rather like the extended theories of gravity name, because that means that we are not modifying anything. It's rather that we are thinking of general relativity as a first step, and then we extend general relativity, okay? I'm not trying to convince you here, but I think that all of us agree in the fact that general relativity is not the end of the story, that we miss a quantum gravity theory, that relativity is only an effective field theory, which is purely classical. It doesn't work when we go down to Planck scales. It doesn't unify quantum mechanics with gravitational interaction. So yes, we do need something beyond general relativity. What extended theories of gravity should do? I mean, what are the minimum requirements that we need to ask extended theories of gravity to satisfy? Well, in my opinion, several of them, but here you can bring your own. First of all, we should ask extended theories of gravity to behave as general relativity in those regimes where we have seen that general relativity works very well. In other words, we need any extended theory of gravity to work well in the solar system, on Earth, on astrophysical scales, etc. Okay, so we don't want to spoil the success of general relativity. The second thing we should ask to any theory of gravity which goes beyond general relativity is that it's able to explain the cosmology in different epochs, in different eras. This is what we need, of course. We need to explain dark energy, or we need to explain, let's say, the expansion of the universe when it was matter-dominated, radiation-dominated, etc. That's why we bring extended theories of gravity, not only to unify quantum mechanics and gravity, but also to explain cosmological acceleration. Ideally, a third point to require to extended theories of gravity is, of course, to ask that we solve problems like the cosmological constant problem, the coincidence problem, the dark energy problem, the dark matter problem, even singularity problems, like even the cosmological singularities, Big Bang, or astrophysical singularities. We wouldn't like to have points where the space-time description fails. We will not be happy having like a singularity at the center of a black hole, roughly speaking. This is, of course, asking too much, but why not? I mean, let's try to see if that works. The end of the slide is, of course, devoted to proposals. And I'm sure that every one of you has like 2 or 3 different theories of gravity you like very much, and 2 or 3 you don't like at all. I have just written here some of them. Okay, so whatever, extra dimension, string theories, scalar tensor, massive gravity, big gravity, whatever, brain wall theories. Okay, so what I'm trying to say is that of course those 3 points up here should be satisfied by any theory you bring to us or to me, and any theory you select would be nice to test if, in this case, neutron stars, quark stars, or even gravitational waves can be predicted, explained, and in agreement with data. That's my point here. Okay, I'm not trying to convince you that any of those theories is the right one. Okay, I've got my preference, but that's not the point of the talk. I'm going to focus in the time I've got left in F of R theories. As I said, I'm not trying to convince you that those theories are the end of the story. I'm just saying what new elements or what new ingredients are coming to town, let's say, when we play with neutron stars and with gravitational waves. And then, yeah, maybe we can apply the same techniques to other theories. Or maybe we can use both neutron stars and gravitational waves to constrain or to rule out or to exclude the viability of those theories. Roughly speaking, probably some of you have already heard about FFR theories. And this is in red at the top, the standard Einstein-Hilbert general relativity axiom that we all have seen in some courses, of course. FFR theories are just, let's say, adding an arbitrary, in principle, of course, a function of the Ricci scalar. That comes from the fact, or that could be understood as a fact of when you do like a quantum inclusion of loops in trying to renormalize general relativity is not renormalizable, but that's why we need to try to add extra terms. The things or the terms which appear the first are like powers of the Ricci scalar or powers of the Ricci tensor or powers of the Riemann tensor. So in 4 dimensions, we can think that the first terms correcting GR are going to be of the form plus R squared plus R to the cube plus something else. So that's why extending general relativity by adding this kind of, I'm going to say powers, but they don't need to be powers, in principle functions, okay, is not that unnatural, okay? Of course, the field equations now look crazy. In red, those are the beautiful Einstein equations. All the line is what you activate when you bring into town this new degree of freedom, let's say. Do you see that you've got extra terms on the right-hand side? You can think of that as a kind of effective fluid which appears, which is a new fluid, which is a curvature fluid, which is like a geometrical fluid. It's not a real fluid, of course. The real fluid is steaming new, but there is some kind of extra contribution from the geometry, which could behave as a kind of dark energy fluid, if you think about it. The second aspect is that the Ricci scalar and the trace of the energy momentum tensor are not related algebraically any longer. This is a very nice result of general relativity, that when you're in vacuum, capital T equal to 0, then your space-time is Ricci flat, and is flat, actually. This is not in principle the fact, or this is not in principle the result that you can obtain in FFR theories. You can be in vacuum, but you can still have a non-trivial curvature, a kind of de Sitter anti-de Sitter, you know, like this is a kind of example. So anyway, those are two main things I wanted to mention about FFR theories, that you've got an effective fluid, extra effective fluid, and that vacuum doesn't mean directly that you are in a Ricci flat space-time. Of course, if you've got field equations, now you can study whatever you want. You can study static fields, you can study spherically symmetric configuration, etc. And this is what I'm going to do. I'm going to consider a metric like this one, which is spherically symmetric, first of all, and which is static. And then I'm going to see if I find solutions. If I find solutions which are going to be my stars. You can also find black holes, of course. But why not to deal with this kind of metric tensor to find neutron stars, okay? And this is what we did, actually. The methodology that I wanted to mention is what I'm going to say now. I'm going to try to be brief. Will do my best. What I'm trying to say here at the top of this slide is that our solar system test only tell us about how big this new contribution of F can be if you evaluate F at the solar system curvature, right? And then probably you read somewhere that the FFR theories need to be smaller than 10 to the minus 6, blah, blah, blah. Yes, but the question is, what is the curvature, what is the scalar curvature of the solar system? That's not very clear, right? The solar system is what, like vacuum, and then you put all the energy at the sun, or, you know. In cosmological scales, a fact that you can think of is that your Ricci scalar is very small, right, on cosmological scales. So what I'm trying to say is that when you consider actions of this kind, like r plus r squared, this parameter a, small a, could be very big because your Ricci scalar is actually very small. What I'm trying to say is that these kind of contributions, even now at the cosmological scales or even at the solar system, could be negligible. But if we go to neutron stars, if we go to stars where the gravitational field is very high, then those contributions could be having some importance. That is my point here, okay? So here I wanted to mention what other approaches people were trying to do when dealing with neutron stars in FFR theories. People in the past were actually passing the ball to the scalar tensor picture. So instead of studying full FFR theories, some of you probably have heard that you can regard FFR theories as a kind of scalar tensor theory. So where you've got a scalar field, an extra scalar field, and then you do the study in that picture. That was done in the past. The full resolution of the problem was done as well, but with two problems, in my opinion, A and B. The first is that those references consider that your only exterior solution to the neutron stars was Schwarzschild. And the second thing is considering that the mass definition that you use in general relativity. I will mention slightly more about this. Is it Schwarzschild a solution outside your star? Yes, but it's not the only solution. This is something that it doesn't happen in general relativity. In general relativity, your only exterior solution of a static, spherically symmetric object is Schwarzschild. In FFR theories, that's not true any longer. So that's something that it's opening a wide amount of possibilities, okay? So what we did then was to study the full differential equation system. So we didn't do any approximation. We didn't expand around any parameter. we were actually, well, matching the interior solution of the star with the exterior solution of the star, of course. And the third point that I think it was quite important is not assuming a priori that Schwarzschild is your unique exterior solution. So those three things are actually what I call the methodology that we were using. So I don't want you to go into details here. The second point might be important. Well, first of all, we want our theory to be stable. Okay, there are different definitions of stability in FFA theories, but yes, we force our models to be stable. That's the first thing I want to mention here. I will not go into details. The second thing is boundary conditions. Yes, when you leave the star, when you are at the edge of the star, the pressure vanishes. This is actually what is defining the edge of the star. If you keep going out, then of course you don't have density nor pressure because you are in vacuum. Okay, so that is very clear to understand. I'm just trying to illustrate how we integrate a system of equations from the center of the star till the edge of the star. Pressure is going to be 0, and then we continue integrating. If we continue integrating, something we want, of course, is to recover asymptotically a kind of Minkowski spacetime. A kind of Schwarzschild, for sure, but even at higher distances, Minkowski, okay? And then we've got a freedom in fixing the initial conditions. The pressure at the center is giving me a family of stars. So if I change the central pressure, I will get one of those curves you saw in the mass radius diagrams. I will be back to that now. But what I'm trying to tell you is this is just a kind of, well, solution of a numerical dynamical system of equations. That's it. It's nothing but that. It solves numerically. Once you've got the solutions, you test that the solutions are correct. That's the only, by plugging in your solutions into the system. That's it. And as I said, not assuming Schwarzschild, just trying to recover asymptotically a Minkowski or an Schwarzschild spacetime, okay? But just asymptotically, not from the very beginning, not as soon as you leave the star. That's a point. So I promised earlier that I would like to mention about the correct label for masses, right? And how we label, once we've got a solution of the equations, what do you call mass? Yeah, maybe some of you are thinking now, yeah, but my goodness, this is the standard thing, right? Is the integral of the density. Nothing but that. Well, let me revise quickly, but at least in several steps, what we mean by mass. In Newtonian gravity, of course, this is what we mean by mass, the density integrated in the volume, right? This is what we've got I don't know, a radial geodesics, and this is what you call the Newtonian mass. The small m is, of course, a test mass, which is orbiting around your test mass, capital M, right? This is what we call mass in Newtonian gravity. In general relativity, actually, the thing, well, the geodesic equation is slightly different, of course. We are not in Newtonian physics any longer. And we need to include the two contributions, of course, the density of the matter and the density of the energy. And as you can see in the integral, given the fact that Schwarzschild is the only solution, you don't find the standard square root of the metric tensor. It's because in Schwarzschild that cancels. That is actually 1. Because, well, if you remember a little bit about the Schwarzschild metric, the coefficients of time and radial coordinates are inverse, one with respect to the other. So there's a 1 here. There's a square root of your metric tensor, but there's a 1 that you don't see here. What's going on in theories beyond general relativity, where you don't have these geodesic equations and you don't have a 1 in your square root of your metric tensor? Well, things are slightly more complicated. If you remember A and B, I'm not going to come back, but A and B were just the coefficient of the metric tensor, okay? So one can parameterize A and B in this way. I mean, you can do it the way you want, but this is just introducing a mass function here. Well, let me not call it mass function. Let me call it a function which depends on r and scales on the denominator like r linearly. And then you can define a function u. As you can see, u is measuring the deviation between a and b to the inverse, and m is a kind of, let's say, function that we want to go to a constant when we are very high distances. The geodesic equation is this now, and now, yes, you can define a kind of asymptotic mass here in blue, and we can call this the gravitational mass, because it's a mass that an observer which is far away will see, will measure, because far away that observer will see a kind of Schwarzschild metric, but far away. Okay, for the asymptotic observer, the mass is going to be this fellow, this limit of this m of f of r. Okay, and yes, we want this asymptotic mass to be constant, of course, not to depend on the distance. We want to be a limit. Okay, but you see that from the Newtonian gravity to here, there is a long way. And the long way is not assuming general relativity and not assuming that your metric is purely Schwarzschild, but it can have other contributions. So yeah, now we can move forward. Now we can go to those two models that I wanted to show you. I've got then equations of motion for a model which is going to be r squared, like Ricci scalar to the square. I'm going to solve the equation and I'm going to extract masses and radius for different equations of state. And then I will see if I can find realistic neutron stars. That's the way to proceed. This is what we get. I mean, general relativity is in blue. You can see it here in every plot. And the other figures, the other mass radius diagrams, the other lines are for different values of this coefficient in your R squared model, this small a. And as you can see, if you change, well, first of all, if you change the equation of state, left, central, and right panel, your mass radius diagrams do change. But also, and that's of course expected, if you change the intensity of your new term, your small a, your mass radius diagrams do change as well. And there are several consequences you can see here. So you can see, for instance, that for each radius, you can find masses, you can find stars which are heavier than neutron stars in general relativity. So they are neutron stars with those equations of state, but they are heavier. So in other words, you've got more mass in the same radius. Okay? In all the figures you see, we have determined those masses that you can see, let's say, here or here or here, using this limit definition. Okay, so those are asymptotic masses which have reached what we call the plateau. They are constant with radius. Okay, they are not the same at every radius, but when you go far away, yes, they are. Okay, they approach a limit. Okay, so why is that? I mean, how can you explain that there is more mass in the same radius and nevertheless this is not a black hole? Is there a paradox? Is there something that you are doing crazily? The answer is no. The answer is that much of the mass that you see as an asymptotic observer is given or is stored, if you want, in the oscillations that the Ricci scalar has when leaving the star. So your metric is not purely Schwarzschild, then there's some kind of energy, gravitational energy around the star. Okay? And when you integrate asymptotically in the very far distance, then this is what you think is the massive content of the star. This is the energetic content of the star. Okay? The final point of this slide actually is saying a lot and nothing, is that as soon as you are, in theory, is different from general relativity, getting two solar masses, neutron stars, is not difficult. You can see it here. I mean, getting two solar masses, neutron stars, is not difficult for very realistic equation of the state. So yes, we are in agreement with observations. We cannot rule out those models from observations, but at least we are in agreement with observations. Another model that we were studying is the so-called Husaviki model. It's another FOFA model. It's much more interesting from the cosmological point of view at late times. And it has this form for n equal to 1, for a parameter n equal to 1, it looks like this. So it behaves like a cosmological constant in some regimes. It provides acceleration. It's a very useful model, okay? So you can read about this model. And so I'm not going to go into details here. Let me go here. And once again, you see different mass radius diagrams. You see that it's not difficult to get heavier neutron stars with respect to the general relativity predicted. And the lower panel down here, I think is very interesting to see, because you can see what the Ricci scalar is doing when leaving the star. This is the edge of the star at this radius, okay? So the Ricci scalar is not immediately 0. It is approaching 0 when you go to higher and higher distances, but it's oscillating. It's having damped oscillations. And those damped oscillations are the ones that later on get reflected in the mass, in the asymptotic mass. Okay, that's a point that I think should be. Gravitational waves. I would like to talk about gravitational waves, but I'm afraid I don't have much time, and I don't want you to hate me by going beyond the time. So what I'm going to do, maybe, if you agree, is going to, what is the relation between what you said about neutron stars in theories beyond general relativity and gravitational waves. And I will then skip what I wanted to tell you about gravitational waves. It's actually more or less the same story that you can find everywhere. Let me go down quickly. I'm not going to go to that. Well, let me stop here. We have so far LIGO collaboration detected at least 3 gravitational wave signals from 3 different mergers of black holes. Those are the data from the first one, which was last year. Those are the black holes which were merging, and the mass of the gravitational wave which was radiated, because you were merging 2 black holes. This is the resulting black hole. The rest of the energy, roughly speaking, went into gravitational waves. Okay. I'm not going to go into LIGO details, sorry for that. That was the first one that I mentioned before. This is the second one. It was later on in 2016. Once again, 2 different black holes, a resulting black hole, and the rest went into gravitational waves. And this is the third, which appeared like 2-3 days ago, actually 3 days ago. And the idea is the same. You've got 2 black holes merging, and the energy which is not in the new black hole that you obtain is transformed in gravitational waves. My point now is the following. As I was telling you earlier, neutron stars in theories beyond general relativity could be much heavier than standard neutron stars in general relativity, or than neutron stars in general relativity, not standard. That means that neutron stars in theories beyond general relativity could be very heavy. And if they could be very heavy, they could also have a merging procedure. And that merging could give rise to gravitational waves. What's going on in general relativity? Well, in general relativity, you cannot get very heavy neutron stars. Therefore, we will not be expecting gravitational wave signals from neutron stars in general relativity, because the signal will be dominated by black holes, mergers, giving rise to gravitational waves. But if you accept that in theories beyond general relativity, neutron stars are very heavy, there are neutron stars in the universe, and they could be more neutron stars than black holes. I'm not going to be into details about that. So that means that neutron stars, and people now are starting to do that, it would be very interesting to study mergers of neutron stars and see what they can tell us about the nature of gravity. This is actually what I wanted to say, and that will be one of my final slides. What about gravitational waves in FFR theories? First of all, are gravitational waves allowed in theories like FFR theories? The answer is yes. This is a pure calculation that someone with experience in determining theoretical gravitational waves in general relativity could do in FFR theories. Yes, they are. The thing is that they've got an extra longitudinal mode. They don't only have 2 transverse modes, they've got an extra one. Those are papers that were showing that. But my point is the following, is like if 2 neutron stars can be merging and they're heavy enough, they could, in principle, release energy in the form of gravitational waves, because we know that when 2 masses are collapsing in a merger, if there is a quadrupole, that quadrupole will give us gravitational waves. Okay? And as I said, gravitational waves from neutron stars in theories beyond GR could be giving us a very good signal of gravitational waves. This is a very simple analysis we did, is that, well, the energy that, let's say, it's remaining and could be emitted in form of gravitational waves could be thought of the total mass that you get at the end minus twice the mass or the mass of the mergers, right? If you double 2m, 2 small m, right? And here on the right-hand side, this is just to show you that if you've got 2, let's say, let me point with a pointer. If you've got 2 masses of neutron stars, okay, either blue or red and neutron stars, they could actually merge into a heavier neutron star, this third one, and the remaining energy could be in form of gravitational waves and could be detected. So neutron stars, if they're allowed to be heavier, and theories beyond GR seems to allow neutron stars to be heavier, they could give us gravitational waves. That is the point I wanted to make here. Conserving the number of baryons, okay? That's something that I wanted to say. So energetically, we are not violating anything. Let me then finish, I'm sorry for running out of time, with what I wanted to say about neutron stars and gravitational waves. First of all, the thing is that now we've got tools to study realistic equations of a state of neutron stars or quark stars or plasma neutron quark stars in theories beyond GR, in a kind of Tolman-Oppenheimer-Volkoff approach, solving the full equations. The second point that I wanted to mention is about the physical mass, and is that we cannot be naive. We cannot be labeling the mass as just the integral of the density. We need to consider that around the star or around an object, there will be an energetic contribution, given the fact that the Schwarzschild is not the only solution. And we need to do that in an intelligent way, to include that and to tell us that they could be neutron stars heavier than expected as in GR, and they're still neutron stars, they're not black holes. The third thing I wanted to mention is that, well, what I did in the past was studying these kind of configurations in 2 interesting FFR models. One is the quadratic Starobinsky model. If we still think that the Starobinsky inflation is alive, why not to test how the Starobinsky model works in astrophysical scales, like neutron stars? And the other model I study is the Husawiki, which is a very popular model in cosmological scenarios. So from cosmology to astrophysics, let's say, from the evolution of the universe as a whole to the study of specific neutron stars configurations. My fourth point is that if the energy available for gravitational wave emission is high enough, maybe what we are detecting now with LIGO is not only black holes. I mean, it has to be black holes if we assume general relativity. But if we allow general relativity to be extended, maybe the signals that LIGO and other detectors are going to see are not only coming from black holes. For instance, LIGSA is expected to measure not only black hole mergers, but to see neutron star, or neutron star, black hole, etc. So here I want to come back to one of my first points, that we are extrapolating that general relativity is valid at least up to 6 to 12 orders of magnitude. And that's a huge extrapolation. So maybe we should allow to free general relativity to be the only theory behind the gravitational interaction and see if both LIGO and LISA or any other gravitational wave detector is telling us something about extended theories of gravity. Because, as I said, F(r) theories of gravity could easily accommodate a 3 to 4 solar masses gravitational wave signal, but not coming only from black holes. That is, I think, very easy. It is actually possible in general relativity, but also from neutron stars. And that will open a new window to study theories beyond general relativity, not only in cosmology or in large-scale structures, but also in now reanalyzing the signals of LIGO and LISA when they are available, and also predicting what are the new features of those signals. Let me finish here, and I'm very happy to answer your questions you may have. Let me come back to the video mode. Thank you.
Thank you very much, Álvaro. So it was a very nice talk. I just like to congratulate for it was very nice. So I guess now we have to pass to the question session. So Please. First of all, just to remind to the people that is following the streaming that you can ask questions to Álvaro in the YouTube chat. So if you are looking in YouTube, just in the right part of your screen is going to appear the chat. So anyway, for the rest of the people that also are maybe following this, are watching this video in the after the live transmission, you can subscribe to our YouTube channel or follow us in Twitter and in Facebook. And let's start with the question for Álvaro from the people of here in the Hangout. So if anybody has a question, please unmute yourself and ask to Álvaro.
Please, don't be shy.
I have a question. I am Diego from Universidad de Antioquia in Medellín. What is the explanation in this kind of theories for the problem of the accelerating universe? Let's say the cosmological constant problem and dark matter.
Yeah, I think that's a very pertinent question, right? I just mentioned that very briefly, but actually. I'm not going to put like a figure, but like around 10 to 15 years ago, people recover F(r) theories of gravity, which were developed actually much earlier as a kind of mathematical exercise. Instead of having the Einstein-Hilbert action, a linear term in the Ricci scalar, people thought, oh, what about adding other terms? When people recovered these theories, like, as I said, around 10 years ago, well, yeah, 15, let's say, that was the main idea. The main idea was to see if one could recover late time acceleration. For instance, one of the first proposals was to extend general relativity with a term which was 1 over r. 1 over r, when the Ricci scalar is small, like today on cosmological scales, it's very big, because 1 over r is the inverse of r, right? But that model was actually proved to be unstable, and the given, oscillations and the given stability test. Then people said, well, not 1 over r, but 1 over r squared. And 1 over r squared, once again, when the Ricci scalar is small, like nowadays in the universe, was actually big, so it was actually fueling, let's say, the acceleration of the universe, and it was stable. So what I'm trying to say is that there are plenty of models, the HUSA wiki is only one, plenty of F(r) models, sorry, which are trying to explain, not only to explain dark energy, but also to be constrained by cosmological data, by supernovae, BAO, large-scale structure, growth of structures, if you go to first-order perturbations. So this is like a kind of school of people developing different models. Of course, the results are model dependent, because if you give me a model, then I find you the best values for the parameters of that model. You can follow, of course, a kind of cosmographic approach and extending general relativity and then trying to constrain in a blind way, in a model independent way, the model which is behind. So for dark energy, what I was trying to say is that there are plenty of models, even models which are trying to unify inflationary epoch, inflationary era, with dark energy dominated era. For instance, if you take like the Starobinsky R square, and then something which is accelerating later on. Take into account that R square, when R is small, like nowadays in the universe, is not going to contribute. Okay, because the square of something small is even smaller. When the Ricci scalar is very big, like in the inflationary era, yes, that can drive acceleration. That was the idea of Starobinsky in adding this f of r at the inflationary epoch. For dark matter, there are also attempts of people trying to, maybe you can understand it this way. If you move to the scalar picture, if you say, look, I don't have a function of the Ricci scalar, but I can think of that as a kind of a scalar field, then this scalar field can behave as a kind of modified gravity explaining dark matter. So yes, I mean, the interest of dark matter in f-of-r theories is smaller than the interest of dark energy, that's true, but there are still attempts to put everything together. I know a couple of references, I can give them to you later if you want, Diego, about dark matter in f-of-r theories. I think not much has been done later on. In dark energy, you can find plenty of investigations or references about dark energy. Of course, and let me finish the question with this, that's not enough, right? Then you need to study, I mentioned that briefly, growth of structures. I mean, how the structures grow when you've got extra terms, your scalar perturbations, your tensor perturbations, your CMB tensor perturbations, your gravitational waves. The existence of black holes, the geodesics, the thermodynamics of black holes. So for every extended theory of gravity, there are plenty of things to be studied and to be seen if they agree with data, or at least, as I mentioned earlier, if you at least recover the GR predictions, at least, right? I mean, at least that you don't spoil what you've got. So there are plenty of tests to see. For instance, even the back reaction, the cosmological back reaction, right? I mean, in general relativity, people have shown that back reaction is not very relevant. It's actually very negligible. But theories beyond general relativity could have more important or less important back reaction effects in the cosmological evolution. So what I'm trying to say is that every single gravitational, astrophysical, and cosmological test that we think general relativity fulfill needs to be not only repeated, but needs to be recalculated with the new equations and then going to the observations. I don't know if this is answering your question.
Yes, of course. Thank you.
Thank you.
Okay, is there another question? Because for the moment I have three questions for Álvaro. The first one is when you are saying that you have that in general relativity you can have masses of neutron stars as large as 2 solar masses, let's say. So that means that it's a kind of a smoking gun to observe a neutron star with mass larger than this threshold, or it's just it can be this effect of have a heavier neutron star can be mimicked because other type of processes that can confuse the observation, like this. You were saying this timing, I don't remember the name, but you were explaining how to measure the neutron star mass from Earth.
Well, I mean, first of all, coming back to general relativity, right? In general relativity, if we've got well, I mean, if the star is non-rotating, the metric is Schwarzschild outside the star. If the star is rotating, then we go to Kerr metrics, but those are very well known, let's say, as well. And then, yes, we can measure the mass of the star. In order to measure the mass of the star, we need to assume, or we need to believe in some kind of equation of state. We need to assume that the star as a fluid behaves in a given way. So what I'm trying to say is that measuring the mass, even in GR, assumes that you are telling me, or that people are convinced that the equation of state is one or the other. Of course, we can ask the QCD experts, and I'm sure that they can give us a range of equations of state, like telling us, look, this is the worst equation of state, and this is the best equation of state. And that range of equation of state within GR, then yes, then it can tell us something about the maximum mass that the neutron star in general relativity can have. This is for sure. In my experience, the agreement at the level of QCD, at the level of equation of state, is not available at the moment. I mean, different schools of people doing QCD will claim that the equations of state are better than the others. Okay, that's fine. What would be nice is to detect neutron stars which has asymptotic masses, the only masses we can measure actually, which are much heavier than general relativity expected ones, even with the most conservative or the less conservative equation of state. Because that, yes, that would be a smoking gun that even in a wide interval of equation of state, general relativity cannot explain that this is a neutron star and not a black hole. That would be true. That would be something as a smoking gun. All the tests, of course, that could be complementary. This is the thing, that now we need to overlap tests and see how we can do things. Those oscillations that I was mentioning that appear as soon as you are in a metric which is continuous at the edge of the star and not purely Schwarzschild. And using standard junction conditions that more mathematical people use to join two space-time regions. Even if you use those pure junction conditions, nothing exotic, not even a brane in between the star and the vacuum, your Ricci scalar is gonna, well, at least decay up to a kind of asymptotic Schwarzschild. But this thing that is not immediately zero will have consequences. For instance, consequences in a kind of transmission and reflection of luminosity signals. Well, sorry, of light signals. This is a quantum effect that when you've got a potential barrier, you will have some transmission and some reflection. So that means that we will be measuring all the effects. It will not be like a plane wave traveling out of the star. So also the geodesics, I mean, how the deflection of light around that kind of stuff. They can also tell us if GR is right or GR needs to be extended. So yes, smoking gun, but not a perfect smoking gun, right? That's my point. I don't know if this is answering that question.
Yeah, I mean, it's one of the ideas, like to find a set of observables that are disentangled GR with modified FR. So another question that that was more related with the question of Diego. In these sets of FR that you test for neutron star, so there were sets that were compatible with this solution that Diego was claiming. I mean, asking about dark energy or dark matter, or there are completely different set of parameters for this attempt.
If you ask me if it's possible to find, let's say, the perfect model, like the model which is able to explain dark matter, acceleration, and inflationary era, probably the answer is yes. But the question is what price you have to pay, because it's very easy to fine-tune your model. I mean, to construct a model with many parameters and then saying, well, my model is perfect. But then, of course, you need a kind of chi-square criteria and quality of chi-square. And of course, that will not be competitive with other theories, with GR, for example, or with GR plus a cosmological constant plus an inflaton, right? At this point, I think that something which is important to mention is that we cannot, having said that, we cannot play the game of considering that the model with less parameters is always the best. Within a paradigm, the answer is yes. But as soon as we open different paradigms, there's nothing wrong, in my humble opinion, if nature decided to have a theory with more parameters than the most simple theory that we think it does work with some problems as GR. So what I'm trying to say is that if a theory, if the underlying theory of gravity at the end of the day has like 3, 4, 5 more parameters than general relativity, but it turns out to be the right one, we shouldn't compare the two theories just by number of parameters. We should be more open-minded in that sense. But in my opinion as well, this kind of tailor-made model, they do exist, but they are very artificial and they don't have any motivation behind. Don't forget that F-over theories are, again, effective theories. Effective theories that they include terms which are expected to appear when you try to renormalize general relativity. But they're not going to be the end of the story either. So they don't have a good motivation, a very deep motivation to choose one model or the other. My final opinion about your question is, or my last comment, let's say, is that they can tell us a lot, because general relativity is a very special theory. It's a theory where the equations are second order, is the only theory with second order equations, field equations. It's a theory where the action is linear in the Ricci scalar, so the exponent is just 1, let's say. And as soon as we go slightly far away from that, as soon as we consider that the exponent in the action is not r to the 1, but r to the 1 point something, let's say that you open a new dynamics. And general relativity is a very particular theory. What I'm trying to say is that by studying to which family of theories general relativity belongs to, we can say something about general relativity itself, because we realize how special general relativity is. Or in other words, which test will tell us in a unique way if general relativity is right or if general relativity can be excluded. Because general relativity does not predict something which is predicted in theories that are, say, close by, but they are completely different, let's say, right? So small departures sometimes are not, they don't mean that the effect is negligible. Maybe, as I said, activating a new degree of freedom in physics may have like extraordinary consequences. And here, F-over theories activate 1 extra degree of freedom. And as I briefly mentioned, in gravitational waves, we've got a longitudinal mode. Well, let's see if we can put more and more constraints to that longitudinal mode not to exist, for instance, right? This is just a proposal, but I find those tailor-made very artificial. I think that you cannot constrain anything at the end, so.
So I don't know if, thank you, Álvaro. I still have one question, but let's give the word to somebody else of the Hangout if they want.
Please,
So,
please.
Yeah, this one.
Okay, I'll risk one. The Pamela experiment and the AMS experiments have confirmed that there's an excess of positrons, right, coming into the Earth. So in principle, usually they say, okay, this could be an indication of dark matter, but then other people say, oh, this could be pulsars, right? So I just found out that pulsars are neutron stars, right? So in principle, your modifications of this, could the AMS data say anything about your neutron stars, the modifications you're having on neutron stars?
I have never thought of that. I think it's a very, I mean it. I'm not trying to please your question. I think it's a very powerful argument, actually. I mean, not argument. It's a very powerful idea to explore, actually, because we are always focusing on pulsars because they can tell us things about cosmology. Of course, they can tell us about a positron excess. But also in cosmology, I mean, for instance, the SK telescope here in Salem, very interested in pulsars, with radio signals that we can get from those positrons, and through that radio signals to constrain cosmology. But rather standard cosmology, I'm gonna say, or cosmology within the lambda CDM model, okay? But I've never thought of this. I've never thought that modification in neutron stars will have consequences in pulsars, yes, but then in the signals, in the eventual signals of dark matter. So I think it's a very good idea. I mean, I don't know at which level. First of all, pulsars are not static, right? I mean, this is my limited knowledge. So what I'm trying to say is that the analysis we were performing, and which was actually, well, I'm going to say one of the first, but also one of the most detailed ones, was of course for static neutron stars. Now, if we want to include like some kind of angular momentum, then we need to generalize it. Shouldn't be difficult. And then, yes, we can generalize the angular momentum, the mass that you obtain, the rate of emission of positrons, the period of rotation, right? And from that, getting fluxes of positrons, well, the whole thing. I mean, in my home institution, there are several people, one PhD student of mine, who is dealing with radio signals from positron excess, so precisely to be measured by SKA. So I think, I mean, I think it's a very good point what you mentioned, and I think what we can do the other way around. We can detect the signals and then trying to, as maybe it's related with the question that Roberto was asking before, like what the data could tell us to constrain the theory, right? So that's probably my answer.
Okay, thank you very much.
Thank you.
So is there any other question? For the moment, I gave the last question that I had. Also, we have to check the questions in YouTube. So one of my question, because you didn't at the end, you couldn't show it presented, but do you expect that also this FR at the end modify the waveform or the shape of the signal that LIGO and gravitational wave detector observe? Like this, the typical signal that is like I don't know how to use the word in English, but at the moment of the merging, because as you were saying during your talk, part of the energy, the gravitational energy of the neutron star, and therefore for the gravitational wave, also is present in the curvature around the object. So you will expect also that the typical wave shape that the LIGO claimed that was because of black hole merger could be modified also in modified gravity models.
This is, I mean, this is I'm going to say a long-term project, because the numerical relativity, right, of gravitational waves in general relativity, I mean, the numerical calculations that the numerical simulations, let's say, to reproduce a merger in general relativity of black holes, etc., is actually extremely complicated. is something that everybody knows, that the numerical relativity for black holes in general relativity is complicated. What I'm trying to say is that in my best understanding, there are no full studies of the gravitational signals in a theoretical way from theories beyond general relativity done in a full way. Of course, if you assume that general relativity is the main contribution and then you add some kind of perturbation, maybe you can get something, you can get some results. But one of my points that maybe I didn't stress enough is that we shouldn't be expecting that general relativity contribution, the general relativity contribution is going to give us the main contribution of this kind of high gravity phenomena, because I mean this example of the Starobinsky model, right? I mean it's negligible, it's very small in cosmological scales, but as soon as your Ricci scalar is huge, general relativity maybe cannot compete, or can compete but at the same level of the corrections. So perturbations are not going to be a good analysis, right? So coming back to your question, I'm not aware of a full derivation of extended theories of gravity for gravitational waves mergers. The theoretical analysis is more like, well, this is the wave, it obeys a wave function, that's it. But not of the merger itself, like when you put two black holes orbiting or when you put neutron stars orbiting. The point that you mentioned that the Schwarzschild metric is not going to be the only one allowed outside, let's say. So in theory, you will have a metric tensor or space-time which is different from Schwarzschild or even from the pure Kerr Schwarzschild, Kerr-Neumann space-time, means that those damp oscillations of your Ricci scalar may have some effects in the gravitational wave signal. So yeah, ideally we would like to see just amplitude and frequency, but maybe those now people are working on those things, like they call it like quantum echoes of gravitational waves. Because of these interference phenomena, there are very good groups working in Lisbon, for instance, in Portugal, in the Netherlands, so in MIT, working precisely of these, I'm going to say quantum effects, but effects in the sense of interference, that they can be important actually because of the scales that you activate. And as I said, this is a long-term project. I don't know if we will be able to do it in a satisfactory way, but at least it would be nice. It would be nice not to rely on general relativity plus corrections, but to rely on the full theory. Unfortunately, or luckily, LIGO people are specialized in general relativity. So sometimes it's quite difficult to tell people working in a domain to move forward or to change, let's say, not to move forward, but to consider a completely different paradigm, because they are so specialized and they do it so well within general relativity that, of course, bringing all the theories, you need to motivate why you bring those theories or how general they are, as I was trying to say earlier. Maybe not f of r calculations by themselves, but more like modifications which could be parameterized in such a way that we could say things for many different theories with the frequency, the amplitude, and all the exotic signals together at the same time.
Yeah, so thank you, Alvaro. So I don't know if there are more questions from this session of Hangout, but we can go to the one in YouTube. So there is one question that is not so clear for my point. I'm gonna just say the first question, that is, is it possible to have torus around black holes? But then after some chatting with this, with the people that are asking this, with the person that is asking that, I think the question is related if in FNR you can have modification to, for instance, to the accretion disk around black holes. Like, for instance, in the galactic center, you expect to have I mean, not in the galaxy, but in new stars, I mean, formation of black holes, you have a disk around the black hole that in some case could reassemble a torus, let's say. And then maybe this modification modifies also the emission in I don't know, X-rays or whatever that this process
I
is.
guess that the answer, of course, in principle is yes, right? I mean, as soon as you, even the standard solutions for black holes, the Kerr-Neumann, the Reisner-Nordstrom, the Schwarzschild, they are modified in the parameters by FOFA theories. What I'm trying to say is that the coefficients get modified, not the powers, not the 1 over r or r squared, etc., but the coefficients, they get modified. Let's say that FOFA behaves as a kind of effective cosmological constant, and the value could be different. The other point that could be relevant is that luckily, or unfortunately, again, these theories have a chameleon mechanism. This is a mechanism that some extended theories of gravity have, telling us that when the density is high, they, let's say, don't have much an effect on the astrophysics. It's only at the very low densities, at cosmological scales where the density goes to cosmological densities, when they do activate the dynamics. Okay, you can read everywhere in Wikipedia as well, like chameleon mechanism. And it was developed in a completely different kind of theories, but later on people realized that FOFA theories, for instance, they do have this mechanism. This is like a kind of screening mechanism. So they are not seen in the solar system, they are not seen in the galaxy, they are only seen, the effect of this dark energy driven evolution is only seen on large scales, which are almost vacuum, roughly speaking, low densities. What I'm trying to say is that ideally, right, I mean, when people do gravitational waves mergers, they consider that the black holes are actually in vacuum, roughly speaking. You only have the two black holes orbiting and then that's it, right? So in those clean environments, then yes, you expect modifications coming from FOFA. When your accretion phenomena happen in a kind of galactic environment, probably you've got these screening mechanisms and the effects are not visible and not present, right?
Okay, so yeah, I guess in that sense was the question that he was asking, but anyway, so let's see if there is no more question from here in the Hangout. This is the last call for questions. If not, I guess we can close this webinar. It was very, very nice, very interesting, in fact. So just to remind to the people, first of all, thanks to Álvaro, and also to remind to the people that are following these low physics webinars that also you can consider to subscribe to our YouTube channel. We are constantly uploading new videos. And then 2 weeks more, we have the next webinar that is going to be about the result of PICO dark matter detector experiment. So I guess from my side is all I wanted to say. Thanks, Álvaro. And
Thank you.
See you in the next time in this low physics webinar. And bye.